Hello, everyone. Welcome. My name is Chris, and this is Colin, and we are two members of the live service team responsible for developing and operating the Simpsons Tapped Out mobile game. We're glad you guys could be here with us today. So we put this quote up first to try and get a cheap laugh, but on another level, it kind of sums up our experiences with AWS quite nicely. Colin and I, we're not DBAs, we're not network engineers, we're a couple of software engineers, and at one time we accounted for 2/3 of the team responsible for developing and operating a service hit by millions of people every day. A situation like this would not be possible without the help of AWS. During the 2.5-year run of Simpsons Tapped Out, our service has evolved in many ways. Reasons for this include performance improvements, reducing costs, and easing operation. Our presentation today is going to cover a few examples of this evolution and show that solutions involving AWS technology not only provide great solutions, but they're almost always easier than doing it yourself. Before we get into the technology side of things, just a bit of a summary of the game for anybody that's not familiar with it. So it's your typical mobile town builder. We originally released on iOS, later added Android and Kindle releases. The premise is pretty simple. Homer has exploded the nuclear power plant, and as a result, Springfield has been destroyed, and you are tasked with the responsibility of rebuilding it. Along the way, you discover new buildings, new characters as you complete quests, level up, all those usual things. The game designers and the licensors were very adamant about making the characters and the story be the star, as opposed to any kind of complex game mechanics. And so as a result, your basic session involves, logging in, collecting money from buildings and characters, advancing any quests, activating new jobs for your characters, and then paying a visit to your friend Springfield. In terms of our release cycles, we have new server deployments roughly every 2 weeks. We have new client content roughly every 2 weeks. This comes in two forms. The first is new client releases. These are the major ones that involve new gameplay mechanics, possibly themed content. In between, we have just DLC releases, which often have new buildings, new characters, new quests, things like that. We have holiday-themed clients throughout the year, the biggest ones being the Halloween and the Christmas clients. We just completed the Treehouse of Horror release for this year. Springfield was being invaded by aliens, and you had to squish them in order to save Springfield. The Christmas event's starting up in a couple of weeks. Not sure all of the different gameplay mechanics, but I do know that the assets get a winter treatment, so everything's covered in snow, and the houses have Christmas decorations for you to activate. We also have other events for things like Valentine's Day and Easter throughout the year. On top of this, during the Simpsons television season, it's not uncommon for us to have episode tie-ins, so 5 or 6 days before an episode airs, we'll release some DLC content that ties in with the episode. So a lot of the times it has some backstory, an advert for the upcoming episode. We just completed one last week for the Futurama crossover episode, for anybody that saw that. So what you see here is a CloudWatch graph of our request count for a 10-day period at the beginning of October of this year. We kind of like this graph because in a span of 10 days, it covers a few events that we see commonly throughout the year. So I'll walk you through a few of those things. So what you see in the first 3 days is the typical usage pattern when a client has either been out for a while and players have exhausted the content or grown tired of the existing client, something like that. You see this day-over-day player decline. This spot here, the marketing team sent out a series of push notifications to try and re-engage some players, so we get a bit of an uptick in our request counts at that time. few days later, this is when we released the Treehouse of Horror client, and as usual, whenever we release a client, there's an uptick in traffic. About a day and a half later, you see a bit of a brief dip in our request count. That was when we activated our forced update mechanic, and what that does is after about a day and a half, anybody who hasn't voluntarily updated the client is sort of forced to do so before continuing with the game. The reason for this is a lot of the times when we release new clients, there's some gameplay mechanic that can only be done with your friends, and it only really works if both you and your friend have the most recent client and the most recent DLC. And what you see at the end is we follow a blue-green deployment strategy, which we'll talk a little bit more about later, and at this point we did a server deployment, and all of the traffic was then moved to a new server environment. So some interesting usage stats. Our highest daily active user count has been recorded around 7.2 million. Our highest peak concurrent user count has been roughly 500,000. We've had request rates exceeding 20,000 per second. And as you saw in that request count graph previously, our player count follows a similar pattern. There's about a 2x player count difference between high peak and low peak traffic. Just a note there, those stats were taken from Treehouse of Horror last year, where our game it was generally considered to be the most popular time for our game. The numbers have dipped a little bit this year, but it's still common to see DAU of 5 to 6 million whenever we release new clients, and request rates around 13,000 per second. Some interesting AWS stats. So we have over 5,000 read and 2,500 write DynamoDB units. Average about 80,000 EC2 instance hours per month, and anywhere between 70 and 150 instances running throughout the day. We have 4 million new S3 objects written per day, about 30 million reads and 30 million writes per day. So just some context here. We store things like the player's session data, friend event data, premium currency balance in DynamoDB, and we store the player's Springfield data in S3. Every 24 hours, a backup job runs and finds all of the lands that have been modified in that previous 24 hours, and will make a backup, which is where the majority of those 4 million new objects per day come from. And I'll hand it over to Colin for a history lesson.
Okay, thanks, Chris. I'm going to go over the game's launch history because it's pretty interesting, and I'll go over some of the few key events. So the game was originally developed by an outsourcing company. Chris and I weren't part of the team. We joined it afterward. There was a predicted massive player engagement of over 10 million DAU. However, the game suffered from a variety of serious issues. Despite planning for a large user base, the system performed very poorly, and as a result, it had poor availability. There were many different problems, and I'll give you one concrete example. The database cluster had 40 shards, and so in order to update a row, the application first had to find the correct shard. But due to a misconfiguration, instead of using a hashing algorithm or some sort of index, it would actually query each shard one by one until it found the correct one. There were data integrity issues. The game logic didn't properly handle concurrent updates, so it suffered from the very basic problem of two users simultaneously reading the same data, making independent modifications, and then trying to write them back. This obviously results in lost updates, but since the game state was being stored as individual data objects with interdependencies, this sometimes resulted in inconsistencies that rendered the data unusable. And so to just give you an idea of the rate of data corruption, it was roughly 2% of the user base per day, so it was very significant. There was no operational telemetry. There was no visibility into the health of the service beyond CPU and network I/O. And then lastly, the deployments were very complicated. It required members from the IT group, the database group, the live monitoring team, the game team, and there were paperwork requirements before receiving assistance from any of these teams was received. And we had a minimum of about 20 minutes of downtime for any deployment. was starting to look like Lisa would be mortified. As a result of the technical problems, the game was delisted from the App Store while solutions were being developed. This put great strain on our relationship with the licensor and drew some unwanted attention from our CEO. At this point, development was moved to our studio in Kitchener, Ontario. The studio had a proven track record of launching and maintaining live services, and the hope was that the new team could turn it around. After all of the critical issues had been addressed, the game relaunched in August 2012. So there was a lot of things that happened in that 4 months. I'm not going to really talk about any of them. Everything that I'm going to talk about is from that point to now. So the system was still in pretty bad shape. It was very complicated, unreliable, and difficult to operate. So all of our subsequent topics will be about how we used various AWS products and features to transform this system into something that is more manageable by a small team. The first topic is about trying to reduce the service downtime as much as possible. These changes took place at different times over the last 2 years. The second topic is about how we replaced our expensive and complicated MySQL cluster with DynamoDB. And the final topic will be about moving the game server to Elastic Beanstalk to simplify deployments, auto-scaling, and failover. Okay, this is the system architecture when the game was relaunched. Even though this is the second iteration of the system, we can consider it to be our starting point, since this is where we were able to start thinking about making optimization rather than just trying to get something that works. So just going over this real quick, on the top right, we have the mobile devices on which the game client runs. Underneath it, we have Origin, which is the EA identity service, so you can use the same user account to play multiple EA games. And then everything else is pretty standard. We have an Elastic Load Balancer. We have a cluster of HA proxy instances, which Chris will talk about a bit later. We have the game servers, which were running on an EC2 cluster, a Memcache cluster, a MySQL cluster, and then we were using S3 for some of the larger game objects. And so it's worth noting that the MySQL cluster, the Memcache cluster, the game servers, and actually also the HA proxy instances were all running in EC2 on manually managed and manually configured instances. So we had a few goals from this point forward. The first problem was that the deployments were very complicated, and so we needed to simplify the process as well as eliminate the deployment downtime. The second goal was to improve scalability and availability. Neither the game servers nor the database scaled automatically, nor did they have failover mechanisms. The database cluster was comprised of 120 EC2 instances, and it would have been very difficult to scale out since we would have needed to reshard them all. And then the third goal was to reduce costs. The database cluster was costing nearly $1 million a year, despite no longer storing the main game data. For most of the last 2 years, our team had only 3 to 4 engineers to handle all of the development and operations. This includes code changes, quality assurance, deployments, and being first-level incident responders. Since we were low on manpower, we needed solutions that used our manpower as efficiently as possible. We accomplished this by adopting various AWS products and features, which will be our main topic for this presentation. Okay, I'm going to turn it back over to Chris for the first topic.
Okay, so one of the things Colin mentioned there was our service stability, so our quest for zero downtime. Just to give you an indication, this is the same diagram that Colin just walked you through. So we'll be focusing on these components here. It's sort of broken up into 2 sections. The first one will be about the game servers and the HA proxy configuration, and then the second half will be about the Origin integration. So problem 1, stateful servers. At the time of the relaunch, all of a player's game state was being cached locally on an individual server. So as a result, players needed to be sticky to that server at all times. We had HA proxy instances behind the load balancer in order to make sure that, or in order to dictate the player distribution. the HA proxy config would hash a player's game ID and be able to direct their traffic to the appropriate server, so that even on subsequent sessions, they would always find that same server. As the set of instances changed, the HA proxy config needed to be updated, and this would alter the hashing scheme, causing some players to switch servers. The additional removal of instances would cause some players to then switch servers, and if they happen to be playing at the time, this is what they'd see. So this is the dreaded BART screen. If you Google BART screen, this is what you will see. Anytime there is an issue with client-server communication in the game, this is most likely what you are going to see. It's so popular that last season, the Simpsons television show even did a parody of it. So anyway, having to re-authenticate in the middle of your session is kind of a bad thing. So deployments at that time were sort of an extreme version of this case. So it would force all active players to have to re-authenticate, causing a 10 to 20-minute interruption in gameplay. The graph you see here, now the data is about 1.5 years old, so it's been aggregated on an hourly level, but in actuality, sort of the player count drop was much more severe, but it only lasted maybe 15, 20 minutes as opposed to what looks like to be 2 hours in this graph. As a result of this re-authentication problem, we needed to take great care to make sure that we only did server deployments at low peak times, and we avoided things like client releases, DLC releases, any marketing promotions. We pretty much had to keep in close contact with those teams to make sure we didn't step on anybody's toes. So obviously we needed to make a change here, and we needed to remove that local caching. So the solution for this was obvious. We had to make use of Elasticache. We had to move all of that locally cached data into Elasticache, make it available for any server so that any client request could go to any server at any given time. We ended up setting up 2 Elasticache clusters, one for the Springfield data for a given player, and then another cluster for all of the other players' data. As a bonus, by doing this, we were also able to entirely remove the HA proxy instances, since we didn't need to keep players sticky anymore. So this rendered the game servers completely stateless, and as a result, we could freely add and remove EC2 instances without affecting the player. So problem number 2 was our auth stability. So as Colin mentioned earlier, we integrate with Origin, our internal, our EA-developed authentication service. And when we first relaunched, whenever Origin was down, we were down. Close enough. Nucleus, fine. Just to give you, the data's a little bit old, but you can see here, this was the minutes of downtime we experienced quarter over quarter whenever the authentication service was down. So we needed to make a change here. So what we wanted to do was put in a mechanism to automatically detect failures and to bypass to some backup functionality whenever those errors were detected. So I'll walk you through sort of what the authentication procedure was. So we'd send our credentials to Nucleus. You'd get an access code back if the credentials were good. You would then use that access code to authenticate against the game servers. That access code would then be validated. If the access code was good, the game server would respond with a game session. Now, the key point here is if the authentication was good, both the client and the server would cache that access code. The game server would cache it in Elasticache, and the client would save it on the device. And this was important for the failure case, where username and password would get sent, and who knows what would happen. The request could time out, we could get some unknown error. Either way, we don't get a valid access code. What happens in this case? We use the saved access code and make the authentication request against the game server. Again, the game server is unaware of anything, any problems, so it'll try and validate the access code. And again, who knows what will happen. With no validation response coming back, the game server will then go and check for any cached access code that it has for this player. If that access code matches the access code that was passed in, you will still get a valid game session. So just a note here, in order to kind of balance stability with security, we only cache those access codes for 7 days on the game server. We don't want 2-month-old access codes being used to get into the game. So how did we do? EC2 instance changes have 0 impact to the player. Deployments have 0 impact to the player. Cache changes have near 0 impact. If we end up having to change the cache clusters at all, then there'll be a little bit of time where you'll have some cache misses and some longer response times, but the player will still be able to play. And auth time has near 0 impact. If you're an active player, you would have no problems getting into the game. Only people that sort of played infrequently or new users would unfortunately still be impacted. I'll hand it over to Colin for the next topic.
Okay. Converting the MySQL cluster to use DynamoDB was one of our most time-consuming but rewarding endeavors. Let me walk you through how we did this. TSTO initially launched with a cluster of 120 extra-large EC2 instances running MySQL. It had a 40 master, 40 read slave, and 40 cold backup configuration. The cluster was operated by a separate team within EA. Deployments which altered the MySQL cluster required coordination with the database team, often requiring time-consuming paperwork and meetings, and it was impossible to change the schema without downtime. We encountered recurring performance issues. Since no one on the team had more than basic knowledge of relational databases, we were unable to effectively troubleshoot these problems. Therefore, we had to rely on the database team to troubleshoot issues, which first required convincing them of the problem's existence and then working with them to develop and deploy a solution. The end result being that too many dollars and too many hours were wasted. So this is the components that need changing. In this section will be the MySQL cluster and its interaction with the game server. Luckily, the existing data model fit well with the NoSQL model, and for the most part, it was simply a matter of remapping various CRUD operations to use the DynamoDB API. The one exception to this was that at the time, there was no support for global secondary indexes, so we had to implement the index using a duplicate table that had a different key schema, similar to how DynamoDB supports this feature today transparently. The difficult part of the migration was moving the vast amount of data in our existing MySQL cluster in a manner that required no downtime. So this was done in several steps. The first was to add application logic that would write to DynamoDB in addition to writing to the existing data store. The result is that the two data stores are now in sync for all active users. We did this for 1 or 2 tables at a time over the course of several releases. However, we still needed to retain the data for inactive users, so the second step was to iterate through every row in every table on every MySQL shard and copy that row to DynamoDB if it didn't already exist. The last step was simply to verify that everything had made it into DynamoDB and to remove the code that writes to MySQL. The conversion process took about 3 months. This includes the time it took to change and test the code, deploy new versions of the software, perform the offline migration, and verify the data. However, we now had a database replacement that was owned and operated entirely by the game team. Quickly going over some of the benefits. Very easy to operate, scale, and maintain this new cluster. It no longer required cooperation with an external team. NoSQL is a much better fit for the type of data we were reading and writing. We had consistent performance, not just consistent, but consistently excellent performance. Coupled with AWS data pipeline and Redshift services, we have the potential for powerful data analytics. And most importantly, our total DynamoDB bill is 90% cheaper than running the MySQL cluster was in EC2. Okay, Chris will talk about the next topic.
Okay, so the last case study we're going to have a look at was our addition of auto-scaling and elastic beanstalk. So for this portion, we'll be looking at the game servers and the load balancer. So there were two problems here that we were really looking to address. So the first, before auto-scaling, we would have to manually provision the number of EC2 instances, and we would have to make educated guesses sort of based on past experiences and often some form of product management estimate. We don't know where they came from. But on top of this, we would have to closely track client releases, DLC releases, marketing events, things like that, to make sure we were properly provisioned before any of these things happened. For major releases like Treehouse of Horror, even after the client was released, we would spend the first few days really keeping an eye on our dashboards to make sure that we were properly provisioned, that everything was healthy, and that we didn't have to adjust the number of instances. And as you saw earlier in the request count graph, it has a very sine wave, very rhythmic pattern to it. And with manual scaling, we had to be provisioned at all times for peak usage. And so there was a lot of wastage going on during the low peak times. The other problem we were looking at was complex server deployment. So at the time of the relaunch, our deployments were done by manually executing some scripts that would launch new instances, deploy artifacts, update our HA proxy instances to redirect traffic to the new deployment. This introduced many opportunities for failure, human error when executing the scripts. We wouldn't get all of the instances we tried to launch. We'd ask for 90, we'd get 87. And then rollbacks were tricky because we'd have to keep the old deployment fully scaled until we were very confident that the new deployment was working properly, and only then could we manually tear it down. So before we could turn on auto-scaling, there's a few things we needed to take care of. So implement a fully stateless game service. We took care of that earlier. On shutdown, any interesting logs we wanted to keep, telemetry, game state, anything that was still on the EC2 instance, we needed to make sure that that was automatically persisted on shutdown. When we were manually scaling, we could make sure that was taken care of manually before tearing down instances. We needed to make sure it was now automatic. And we needed to determine our auto-scaling criteria. We did a number of load tests. We had to tweak it a couple of times in our first few deployments, but we ultimately settled on a policy based on CPU utilization that was aggressive enough to rise and fall with the natural player count, but there was still some manual intervention required if there was some big abnormality in our player count. So what you see here is our healthy host count over that same 10-day period that we were looking at earlier for the request count. Now, we're in 3 availability zones, so the actual number of instances running is 3 times the number you see here. So at this time, we have auto-scaling in place, so you can see our number of instances rising and falling in that same rhythmic pattern. If we didn't have it, this would be an example of what the provisioning might have been set at. And so you can see the big gaps there, the big white areas where we would be wasting EC2 instance hours by having to manually provision it this way. The other thing I wanted to highlight was, so this was the marketing activity we talked about earlier. The auto-scaling policy was actually able to keep up with that aggressive increase. So we were good this time. Colin's going to share something later where we weren't so lucky. So having auto-scaling integrated certainly made the lives of the server team much easier, but on top of that, it also saved us some money. So you can see here, this is month over month, our EC2 instance hours, and you can tell where we added auto-scaling. We had a drop of 30% in the number of instance hours used per month. So the other half of this was the complex deployments, and for that we turned to Elastic Beanstalk. So as I was mentioning before, we like the idea of the blue-green deployment strategy. We keep a fully scaled production environment, a minimally scaled pre-production environment, and the ELBs are fully warmed in both environments. And the reason we like this is because it facilitates testing really nicely. We can put the new server code on the pre-production environment, have QA test it out before we fully scale it up, and then complete the swap. It also facilitates an easy rollback. You just redirect the traffic back to the other deployment. So yeah, 3 basic steps now to our server deployments. We upload the artifacts, we scale up the pre-production environment, and then perform Elastic Beanstalk's URL swap to cut over to the new deployment. And as I mentioned, rollbacks are as simple as just doing that URL swap back to the previous environment. If it's been a while since traffic was hitting the old deployment, we might have lost a number of instances due to auto-scaling, so we might just have to top it up, but otherwise, it's just that easy. So the benefits, if it isn't already obvious, it's greatly simplified our deployments. They can now be done entirely within the game server team and often by just a single person. The opportunity for human error is greatly reduced because Elastic Beanstalk is doing a lot of the heavy lifting for us, and deployments can now often be completed and verified in under 20 minutes or so. The other benefit is the dashboards that Beanstalk provides you. So it's got a nice monitoring dashboard coupled with our own custom dashboards. We have unprecedented visibility into our service. We're always the first to know of any issue with our service, and we are always the first to respond to any issues with the service. And so now Colin will tell us some stories.
Running a live service is often very exciting when things don't go according to plan. I'm going to share a couple funny stories about problems that arose unexpectedly and how we were able to solve them quickly. Whacking Day was a major content release in spring 2013. The goal was, unsurprisingly, to whack snakes. But before I talk about this event, I first have to review the existing system mechanics. In TSTO, you can visit a friend's town and perform actions. These actions generate events which your friends can see and acknowledge. For every event generated in this manner, we have one database write. When your friend acknowledges the event, there is one database delete. There's a limit of 3 events per friend per day. And throughout the entire system, we had pretty low DynamoDB read and write throughput on this table of about 100 read and write units respectively. For Whacking Day, the user's goal was to collect eggs. They could collect over 100 per day. They could place any number of eggs in a friend's town, and each egg placement generated an event. Okay, as you can see on the bottom left, this is a pretty typical example of what a user would do at any given time. Okay, and because of this, the consumed throughput grew by an order of magnitude. Fortunately, we were able to detect this increase in time due to CloudWatch alarms, and we were able to increase the provisioning in time to prevent user impact. This underlines the importance of having DynamoDB auto-scaling, so we made sure to put that in place. There's some open source tools that you can use now, but at the time, we had to write our own auto-scaler. And then the more important action item was to be more involved in the content design process so that we could give other project members greater insight into how game features affected the service. Okay, the next story. Occasionally, marketing will send push notifications to all users, and it's designed to inform them of a key event, such as a content update or an item sale. This is usually done by dividing the entire player base into 24 segments, sending notifications to 1 segment per hour. It's done this way in order to avoid large spikes in traffic. In one of our recent updates, a client was released which contained, unbeknownst to us, a built-in notification schedule which was independent from the usual marketing process. The first notification awarded players with donuts and urged them to come into the game and claim their prize. The notification was extremely effective. The problem was that it went to every single player in the world at the exact same time. This led to what was effectively a DDoS. As you can see, the system couldn't handle the strain, and the player count dropped to almost 0. It can't really be seen in this graph, the one on the top left, because each data point is in 5-minute intervals, but it turns out that the player count had doubled in under 5 minutes. For the graph on the right, you can see that we lost about 30 instances. You can see EC2 auto-scaling trying to kick in. That's the little bump after the drop, but it couldn't keep up with the increasing traffic. And so when we realized what was happening, we had to manually double the instance count, which is what you see on the far right with the large spike in instance counts. Sorry, I forgot something. There's an obvious lesson here, which is to avoid telling all your users to log in at the same time. But there's a more widely applicable lesson in that you should always think carefully about how marketing activities can impact your service and to make sure that it's done in a safe manner. So I'm just going to review the changes from the relaunch to the present day in the architectural diagram. So we didn't talk too much about it, but one of the first things we did was move the manually managed Memcache cluster to Elasticache. That was pretty easy. As Chris talked about, we made the game server stateless, and so we were able to remove the HA proxy cluster. We changed the MySQL cluster to use DynamoDB instead. And then we added Elastic Beanstalk. Regarding the original problems we wanted to solve, for complex deployments, they're now extremely easy using Beanstalk. For the auto-scaling and failover, we now have auto-scaling and automatic failover on every component. And then for the expensive database cluster, we were able to replace it with a very cost-effective solution. AWS allows our team to be autonomous and efficient. If there's ever a problem with the system, we're able to single-handedly troubleshoot, develop, and test and deploy a solution, all within a few hours. Whether it's by developing new products or features or reducing the cost of existing features, AWS keeps getting better. We're always on the lookout for new features to improve our service. Like Chris said at the beginning, we're not DBAs and we're not network engineers. We're a team of generalists running the live service for a game played by 6 million people per day, and it would be impossible without AWS. Thank you, everyone, for attending. You can give us your feedback. This is GAM302. And thanks for attending.